Today, we are diving into one of the most important concepts in all of statistics, the p-value. By the end of this lesson, you will be able to interpret the p-value of a hypothesis test for a population proportion and explain what it means in the context of statistical evidence. To understand a p-value, we must start with the assumption that the null hypothesis is true. When we assume the null hypothesis, we create what is called a null distribution. This represents the probability distribution of the test statistic if the null hypothesis were actually reality. The p-value is the probability of obtaining a test statistic as extreme or more extreme than the one we actually observed, in the direction of our alternative hypothesis. Think of it as a measure of how surprising our data is. If the p-value is very small, it means our observed result would be very unlikely to happen just by chance if the null hypothesis were true. The way we calculate a p-value depends entirely on our alternative hypothesis, often denoted as HA. Let's look at the first case. If our alternative hypothesis is that the proportion is greater than some value, we look at the right tail. The p-value is the probability of getting a result at or above our observed test statistic. If our alternative is less than, we look at the left tail. The p-value is the probability of being at or below the observed value. Finally, if the alternative is not equal to, we have a two-tailed test. We find the probability in both extremes, the area less than the negative absolute value of our statistic, plus the area greater than the positive absolute value. In every case, we are measuring the extremeness of our data relative to what we expected under the null hypothesis. Sometimes, we don't use a theoretical formula. Instead, we use a simulation to create our null distribution. In a simulation, the p-value is simply the proportion of simulated trials that resulted in a value as extreme or more extreme than our observed data. If we observed a result of 0.6 and we ran 100 simulations, we would count how many of those dots are at or above 0.6. If only 2 out of 100 simulations reached that value, our p-value is 0.02. This tells us that if the null hypothesis were true, a result like ours would only happen 2% of the time by pure random chance. When you interpret this, you must always include the phrase, assuming the null hypothesis is true. It is the foundation of the entire calculation. Now, let's talk about what the p-value actually tells us about our evidence. A small p-value indicates that the observed data is unusual if the null hypothesis were true. Because it is so unlikely to happen by chance, a small p-value provides strong evidence for the alternative hypothesis. The lower the p-value, the more shocking the data is, and the more convincing the statistical evidence becomes. On the other hand, if the p-value is not small, usually meaning it is above a certain threshold, like 0.05, the observed value is not considered unusual. In this case, we say we failed to provide convincing evidence for the alternative hypothesis. It is a common misconception to say that a large p-value proves the null hypothesis is true. It doesn't. It simply means we haven't found enough evidence to move away from it. Think of a court trial. A not guilty verdict doesn't mean the person is innocent. It just means there wasn't enough evidence to prove they were guilty. Statistics works the same way. To make this concrete, let's walk through a full example. Suppose a company claims that 80% of its customers are satisfied. A consumer group suspects the true proportion is actually lower. The group surveys 100 customers and finds that 72 are satisfied. They calculate a p-value of 0.023. How do we interpret this? Assuming the true satisfaction rate is 80%, there is a 2.3% probability that a random sample of 100 customers would result in a satisfaction rate of 72% or lower. Because 0.023 is quite small, this provides convincing evidence that the true proportion of satisfied customers is indeed less than 80%. The result is statistically significant. Notice how the interpretation connects the assumption, the null is true, with the probability of the observed result in the direction of the alternative. Let's look at another example involving a two-tailed test to see how the interpretation changes. Suppose a coin is claimed to be fair, meaning the proportion of heads should be 0.5. A student suspects the coin is biased but doesn't know in which direction. The student flips the coin 50 times and gets 32 heads. This is a sample proportion of 0.64. After running the test, the resulting p-value is 0.048. To visualize this, we look at a normal curve centered at 0.5. We shade the regions in both tails, one for values greater than or equal to 0.64, and one for values less than or equal to 0.36. To interpret this, we would say, assuming the coin is fair, there is a 4.8% probability of getting a sample proportion at least as far from 0.5 as our observed 0.64. Because this p-value is below the common 5% threshold, we have convincing evidence that the coin is not fair. Note how we included both extremes in our interpretation because our alternative hypothesis was not equal to. For our final example, let's look at a case where the p-value is large. Suppose a high school principal claims that 90% of students support a new dress code. A student journalist thinks the support is actually different than that. The journalist surveys 50 students and finds that 43 support it, which is a sample proportion of 86%. The calculated p-value is 0.396. Here we see a normal curve centered at 0.90. The observed value, 0.86, is very close to the center, leading to large shaded areas in both tails. How do we interpret this p-value? Because 39.6% is a very high probability, this result is not unusual at all. It could easily happen by random chance. Therefore, we do not have convincing evidence that the true support level is different from 90%. Remember, we haven't proven the principle is right. We just haven't found enough evidence to say they are wrong. In summary, you've learned that a p-value is a probability calculated under the assumption that the null hypothesis is true. It measures how extreme our data is, and it provides the evidence we need to support or fail to support our alternative claims. You are now ready to interpret p-values in any context,